Stand on the top deck of a large cruise ship, close to 20 stories above the waterline, the deck stretching wider than most highway lanes in either direction. And at some point, your brain does something inconvenient. It starts doing the math. The horizon isn't flat. The ocean is moving underneath you, and somewhere in the back of your head, a very basic physics question assembles itself. How exactly is this thing not tipping over? The obvious answer feels satisfying for about 30 seconds. It's enormous. It weighs over 100,000 tons on the larger ships. Things that heavy don't just tip over. Except that's not actually the answer. Mass alone is one of the worst explanations for ship stability. 100,000 tons of steel arranged in the wrong configuration would go over just as fast as a rowboat. The question isn't how heavy it is. The question is where the weight sits, what the hull is doing at any given angle of lean, and, this is the part most people don't think about, what's actively running below decks right now to keep it there. The answer turns out to be a layered system. Some of it is passive, built into the geometry of the hull before the ship ever touches water, never switched on because it never needs to be. Some of it is active, running continuously from the moment the ship leaves port to the moment it returns. And some of it, and this is the part that's quietly amusing, involves you personally. Start with the geometry. When a ship heels, tilts sideways, two forces immediately start arguing about what happens next. Gravity pulls the ship's center of mass straight down. Buoyancy pushes up through the center of the submerged volume, which shifts dramatically toward the lower side the moment the hull begins to lean. If the buoyancy force's line of action falls outside the ship's center of gravity, you get what naval architects call a righting couple, a force pair that spins the ship back upright. If it doesn't, you get the other outcome. The invisible point where these forces meet has a name, the metacenter. The key metric is the distance between the metacenter and the ship's center of gravity, called the metacentric height, abbreviated GM. A large GM means the righting force kicks in fast and hard, which sounds exactly like what you'd want. Here's where the assumption starts to crack. You'd expect engineers to maximize GM, push it as high as the hull allows. They don't. They deliberately bring it down. A very high GM produces a short roll period. The ship rights itself so fast and so violently that the motion becomes a rapid, snapping lurch back and forth. Dishes leave tables, passengers fall, structural stress accumulates across the voyage. A cruise ship built for maximum initial stiffness is not a safer ship. It's an uncomfortable and mechanically punishing one. So naval architects tune GM into a deliberate comfort window, enough restoring force to handle the scenario, gentle enough that the roll feels slow and measured. That slight, almost graceful sway you feel when the ship moves in open water, it's not the hull being sloppy, someone calculated it. The real safety net at large heel angles isn't the initial GM figure anyway. It's something called the GZ curve, a plot of the righting lever across all possible heel angles, and specifically the area underneath it. That area represents the total energy the ship can absorb before it stops coming back. Naval architects call it dynamical stability, and it's what regulators are actually checking when a ship has to prove it won't capsize. Not how stiff it feels tied up at the pier, how far it can lean and still recover. Which brings us to the part of the hull doing the heaviest lifting, the beam. Beam means width, and on a large cruise ship, that number can reach 200 feet or more on the largest ships. As the hull heels, the submerged cross-section shifts sharply toward the low side, and the wider the ship, the further that shift goes and the stronger the righting force it generates. Beam does more stability work than any active system on board. It does it for free, permanently, without a single kilowatt of electricity or anyone monitoring it. The weight distribution is the other piece of the passive architecture. Engines, fuel tanks, ballast water, heavy machinery, all of it rides in the double bottom and lower decks, as low in the hull as the designers can manage. Staterooms, pool decks, restaurants, entertainment venues, those ride high but light. The ship is built as a deliberate pyramid of mass, wide and heavy at the base, lighter as you go up. Moving the fuel load to the upper decks on a vessel this size would shift the center of gravity by several meters and undermine the entire stability picture. The weight placement is not incidental. It is structural logic encoded into the ship's architecture before the first steel plate is cut. So before any active system ever turns on, the hull is already doing its job, running on geometry, not electricity. The active systems exist to manage the comfort layer and the edges. The one you've probably heard of is the fin stabilizers, retractable underwater fins mounted on either side of the hull, controlled by a computer that reads the ship's roll motion in real time and adjusts the fin angle to generate a counteracting force. Think of them as underwater wings, creating lift to push against the roll. Effective, responsive, and on a large ship, a multi-million-dollar installation that cruise lines market heavily as a passenger comfort feature. There's a catch though, and almost nobody knows it. The fins only work when water is flowing over them. They are wings, and wings require flow to generate lift. On most ships, when the vessel slows or stops at anchor and port during tender operations while small boats are ferrying passengers ashore, the fins retract and go offline. The roughest moments you'll experience on a cruise almost always happen when the active comfort system has been switched off. That rolling swell rocking the ship while you wait on the tender deck isn't rougher water than yesterday's open sea. It's the same class of motion minus the equipment designed to smooth it out. Speed, it turns out, is a stability input that never makes it into the brochure. Some ships use a secondary system for this exact gap: anti-roll tanks, large tanks of water plumbed in a U shape across the ship's width. As the ship heels, water sloshes to the opposite side and pushes back. Slower to respond than fin stabilizers, but they work at rest, which makes them genuinely useful on itineraries with long anchor times. Now the ballast. Distributed throughout the hull are tanks that can hold or release seawater to adjust the ship's trim, heel, and stability picture in real time. The officer managing all of this, typically the chief officer, runs load planning software that tracks displacement, GM, the GZ curve, and live heel angle from instruments called inclinometers mounted in the hull. When 3,000 passengers board with luggage, when fuel is pumped in, when provisions are loaded, the stability picture shifts and the officer is recalculating and rebalancing. Before departure, a formal stability booklet documenting that the ship meets minimum intact stability criteria has to be completed and filed with the flag state authority. The captain doesn't leave port without it. Which raises the question of what those stability calculations actually have to account for. And here is where it gets quietly interesting. You're a stability variable. Not individually, but when several thousand passengers crowd the starboard rail to watch a glacier calve or a pod of whale surface, the ship develops a measurable list, a real heel angle that shows up on the inclinometers and appears in the stability officer's live data. The calculation is already in the booklet. The load case, passengers massing to one side, is something the naval architects modeled and planned before the ship was ever launched. You and every other person at the rail are, collectively, a loading condition the ship has already solved, which raises the obvious question about extreme scenarios. What about a genuinely large, unexpected wave? Could something dramatic in the open ocean push past the system's limits? The realistic threat isn't the classic broadside capsize people tend to picture. The actual concern is a phenomenon called parametric rolling, a resonance effect where wave crests and troughs pass the hull at a rhythm that alternately builds and collapses the ship's righting force, allowing roll to compound rapidly from a few degrees to dangerous angles in just a handful of cycles. Modern ships monitor for it and navigate out of it, adjusting speed and heading to break the resonance before it has room to grow. This scary scenario is real, but the answer to it is a course correction, not mass. If you've ever noticed a subtle list developing on a cruise, furniture at a slight angle, something rolling slowly across the table, here's what's already happening while you're registering it. Below decks, ballast is transferring. The inclinometers caught it first. The officer is looking at it. If it's correctable, it's being corrected, probably before anyone reaches for the public address system. The ship's response has already started before anyone tells you anything. That's the part that tends to reframe the whole picture once you see it. The stability management on a cruise ship isn't emergency response. It's background infrastructure, load computers, ballast adjustments, fin deployment, inclinometer readings, running continuously on every voyage, on every ship, in every sea state, every hour from departure to return. It doesn't activate when something goes wrong. It runs to make sure something doesn't. Next time you're at the Lido deck rail and you feel that almost imperceptible lean toward the port side view, know that the stability officer already sees it. The ballast pumps are probably already running. The whole invisible system is doing exactly what it was designed to do while you hold your drink level without giving it a thought. That slow, gentle sway is not the ship losing its balance. It is the ship being managed. That's another one for the cruise files. If you want to learn more about what goes on behind the giant cruise ships, everything from the scams on board to the secrets below deck, subscribe, like, and share. Thanks for watching, and I'll see you in the next one.